So as promised, I'm going to work a few applications of linear inequalities with two variables. Let's begin. So Portland Parks and Recreation is constructing a rectangular ferret run within a small neighborhood park. The ferret run must have a 2-meter wide gate. The department has 298 meters of ferret fencing, but may need some of the fencing for other projects. We want to write an inequality that represents the situation, graph the solution set, and discuss some feasible solutions. So let's start by writing our model. What I need here is to think about the perimeter of the ferret run. So when I think about perimeter, I need to think about the length and the width of the rectangular ferret run. So I'm going to let L and W represent the length and width, both measured in meters, of the ferret run. Now, when I think about how much fencing is going to be used, I'm going to need fencing for both lengths, for one width, and over here I'm going to need W minus 2 meters of fencing. So when I write my model, I want to add up all these lengths, and that needs to be less than or equal to the 298 meters of fencing that are available. So let me write my model. So I have 2 times the length plus the width plus the width minus 2. This needs to be less than or equal to 298. Let me simplify this model a little bit. I have 2L plus 2W, and I'm going to add 2 to both sides, so that's less than or equal to 300. Dividing both sides of the inequality by 2, that's a positive number, so the sense of the inequality will remain the same. So I have the length plus width needs to be less than or equal to 150. So there's the model. Now let's graph the solution set. So I'm going to start by graphing the boundary line. The boundary line in this case is L plus W equals 150. It's going to be pretty easy to find some solutions to this equation. I think I'm going to put the width of the ferret run on the horizontal axis and the length of the ferret run on the vertical axis. So let me just take a moment to label my axes. And now let's work to find a couple of solutions that we can use to graph the boundary lines. Well, the ordered pairs are going to be of the form WL. Let's find the intercepts because they're so easy. When W equals 0, L equals 150. And when the length is 0, W equals 150. So this allows me to think about a scale. I think I'm just going to use a scale of 25 on both axes. So labeling every other tick mark, now I'm good to go. So I'm going to label the 2 intercepts of my boundary line. And I'm going to connect my boundary line. In this particular inequality, I have L plus W is less than or equal to 150, so I'm going to include the boundary line. So now I want to think about what part of the coordinate plane satisfies the inequality. Well, let's first take a couple of solutions on the boundary line. For example, the ordered pair 75, 75 is on the boundary. This means that we could create a square ferret run, and we would use all 298 meters of fencing. We could also make a rectangular ferret run that's 50 meters wide and 100 meters long. And in this case, we'd use all the fencing for the ferret run. But suppose I didn't want to use all of it. I wanted some left over for another project. Well, there are a couple of other points that I could choose. For example, here I have a width of 50 and a length of 100. If I decrease the length, I will be using less fencing. So if I decrease the length, for example, if I choose the point 50, 75, I won't be using as much fencing. I could also start at the point 50, 100 and decrease the width. For example, if my ferret run is only 25 meters wide and 100 meters long, I'll be using less fencing. So I can see the points that make sense in the context of this problem are points that lie below this line. Now when I shade, I'm going to shade just points in the first quadrant. And the reason why I'm doing this is because in the context of the application, both the length and the width need to be greater than or equal to 0 because they have meanings, they measure a distance. Now let's summarize and discuss these solutions. So we want to sort of make a conclusion about what we just saw in the graph. So one of the things we noticed is that Portland parks can construct, for example, because there's lots of possibilities, a square ferret run, 75 meters by 75 meters, or a rectangular ferret run, 50 meters by 100 meters. And in this case, they'll use all their fencing. But there were a couple of possibilities we looked at that didn't use all the fencing. To have some fencing left over, a ferret run that is 50 meters by 75 meters or 25 meters by 100 meters could be built. Now there were a lot of other possibilities that we didn't discuss. We're just looking at a few possible cases here. Let's do another application. The elevator in an apartment building has a capacity of 1,600 pounds. Assuming that the average adult weighs 160 pounds and that the average child weighs 50 pounds, write an inequality that shows the number of adults and children that can ride in the elevator at one time. Graph the inequality and discuss some feasible solutions. So we want to start with a model of this problem. So when we think about this problem, we have to think about keeping the weight below the capacity of the elevator. So the elevator capacity is what's going to limit us in this problem. And what we need to do is make sure that the weight of the adults plus the weight of the children, that the sum of those two weights is less than or equal to the elevator capacity. So let's think about how we would determine the weight of the adults. We're given the information that on average an adult weighs 160 pounds. So if we multiply the number of adults by the average weight, that will tell us the total weight of the adults. We can do a similar calculation for the children. So what I need here for variables are the number of adults and children that will be in the elevator. So I'm going to let A represent the number of adults and C represent the number of children. So using my verbal model, it will be very easy to write down an inequality. I take the average weight of an adult and multiply it by the number of adults. And I'm going to add to that the average weight of a child and multiplied by the number of children. And that has to be less than or equal to the elevator capacity. So now we have an inequality that we can graph. So here I need to, again, graph the boundary line. And the boundary line is the equation 160A plus 50C equals 1600. I'm going to choose to put the number of adults on the horizontal axis and the number of children on the vertical axis. So the ordered pairs that I'll be using will be of the form A, C. Let's see if we can figure out what the intercept should be. If C is 0, then A needs to be 10. So the point 10, 0 will be on the graph. If A is 0, then C is going to be 32. So the point 0, 32 is on the graph. So this will allow me to choose a decent scale to draw the boundary line. I think I'm going to choose a scale of 1 on the horizontal axis because I need to get out to 10. And I'm going to use a scale of 4 on the vertical axis because I need to get up to 32. And 4 times 8 is 32, and it looks like I have enough boxes to do that. I have 8, 16, 24, 32, 40. So graphing the boundary line, I will use the 2 intercepts. The boundary line is included in this model. Now we want to think about which ordered pairs in the plane will be solutions to our inequality and which of these will be feasible in the context of the problem. Well, let's look at our 2 intercepts. Our 2 intercepts tell us that if the elevator has 10 adults and no children, it will be at capacity. So everything should be okay. Or the elevator could have no adults and 32 children, and it would be right at capacity, and everything would be okay. Let's look at some other combinations on the boundary line and use that to think about solutions to the inequality. So on my boundary line, I see the point 5, 16. This means the elevator can hold 5 adults and 16 children and be right at capacity. But let's think about getting below capacity a little bit. From this point, I can move to some other points in the coordinate plane. For example, if there were fewer adults and the same number of children, the weight should still be below the capacity of the elevator. So I think I'm going to choose the point 316, and I can see that that should be part of my solution set. The other thing I could do is if I keep 5 adults in the elevator, I could decrease the number of children. So for example, I could have 5 adults and only 10 children. That will also be in my solution set. So I'm going to shade, again, under the line, recognizing that the number of adults and the number of children have to be positive. But in this situation, it's a little bit different than the ferret run problem. Here, the only points that make sense in the context of the problem are points where both coordinates are integers, because we have to have an integer number of adults and an integer number of children in the elevator. So we've discussed a few solutions. Let's state a conclusion. So the two intercepts gave us some information, as did the point 516. These were all the points where we were at capacity. So the elevator is at capacity with either 10 adults or 32 children, or a combination of 5 adults and 16 children. But we also talked about some solutions where the weight in the elevator would be below capacity. There are several combinations for which the weight is below capacity. For example, 5 adults and 10 children. That corresponds to the point 510. Or 3 adults and 16 children. Now there are some other reasonable solutions, but we just discussed a few of them. Let's do another example. An urban post office must be able to service at least 96 customers per hour. Regular clerks service 24 customers per hour, whereas special services clerk service 12 customers per hour. Write an inequality that gives the number of each type of clerk needed to meet the post office's requirements, graph the inequality, and discuss some feasible solutions. So we're going to start with a model of this staffing problem. Now here, we have to service at least 96 customers per hour. If we service more, or if the post office services more than 96 customers per hour, they'll be meeting their requirements. So this inequality is going to be a little bit different than the ones we just did. Now we know how many customers can be serviced per hour by the regular clerks and the special services clerks. So if we add up the number of those customers, that needs to be greater than or equal to 96. So we have a place to start. Now let's think about what the unknowns are here. The unknowns are the number of each type of clerk that's needed. So I'm going to let M represent the number of regular clerks and N represent the number of special services clerks. So we have M regular clerks. How many customers per hour can those M clerks service? So each regular clerk services 24 customers per hour. So if we take 24 customers per hour and multiply it by the number of regular service clerks, that will tell us how many customers are being served. So that's going to be 24M. Now we have to add that to the number of customers being served by the special services clerk. Well, they service 12 customers per hour. So now we have an inequality, which is a little bit different than the ones we just considered. So now let's graph the solutions to this inequality. Once again, we're going to start with the boundary line. And the boundary line is 24m plus 12n equals 96. Again, pretty easy to graph this. Also notice that the equations, the linear equations we're getting, are in standard form. So we're seeing some situations where standard form does arise in the context of applications. So I'm going to label my axes m and n, and this will be the number of regular clerks, and n will represent the number of special clerks. So the ordered pairs for this line are going to be of the form mn. Once again, I'm going to find the intercepts. So when n equals 0, m will equal 4. So I know that the ordered pair 4, 0 is on the graph. Similarly, when m equals 0, n is going to equal 8. So I've got my intercepts, I'm ready to graph. I think in this situation, I'm just going to use a scale of 1. Plot my two intercepts. Here, again, the boundary line is included in the solution set. And so now let's talk about some feasible solutions and talk about which side of this line we need to graph in the context of the problem. Well, the intercepts are meaningful. If the post office works with just 4 regular clerks, they can exactly meet their requirements of servicing 96 customers per hour. On the other hand, if they work with just 8 special services clerks and no regular clerks, they can still service 96 customers per hour. There's some other solutions on this line. For example, if they have 1 regular clerk and 6 special services clerks, they will still be able to service exactly 96 customers per hour. But let's suppose they want to service some more. Then what they can do in this situation is just maybe hire a few more clerks. So for example, if I had 4 regular clerks and 6 special services clerks, I should be able to service even more customers, more than 96 customers per hour. If I want to even things out a little bit and have 4 of each type of clerks, that's still going to work. So my solution set in this case are going to be points to the right or above this line. Again, only the ordered pairs with integer coordinates are really going to make any sense in the context of the model. So now let's state a conclusion by discussing some of these solutions we just found. So we saw that if the post office used 1 regular clerk and 6 special services clerks, they could exactly meet their needs. But they probably want to service more than 96 customers per hour if they can. And for that, they'd have to do some extra hiring. The 2 possibilities we talked about were hiring 3 more regular clerks or hiring the same number of regular clerks and special services clerks. So to service more than 96 customers per hour, the post office could hire, and this is just for example because there's a lot of possibilities we didn't talk about, 4 regular clerks and 6 special clerks, or 4 regular clerks, and let's make a little more room, and 4 special clerks. Logan has an expense account. $400 deposits are made into the account, and Logan uses the $50 fast cash option to make withdrawals. What combination of deposits and withdrawals will ensure that Logan maintains a balance of at least $100? Now clearly we're going to use an inequality here again, because we're being asked what combination of deposits and withdrawals will ensure that Logan maintains a balance of at least $100. He may want to have more money in his account than $100. So this requires an inequality. So let's start with a model. We've got 2 unknowns here, the number of deposits and the number of withdrawals. So let's define variables for those unknowns. So I'm going to let D represent the number of deposits and W represent the number of withdrawals. So I know that I want the money in the account to be greater than or equal to $100. But let's think about what that should be. We want the amount deposited minus the amount withdrawn to be greater than or equal to $100. More money's got to go into the account than's coming out to maintain a positive balance. So now let's think about how we can use algebra to model the amount deposited and the amount withdrawn. If we make D deposits and each deposit is $400, then the amount deposited is 400D. And if we make W withdrawals, and each time we are withdrawing $50, then we are going to be subtracting from that 50W. Now in this situation, if I think about the boundary equation in standard form, 400D minus 50W equals 100, and I think about the trick I've been using in all these problems of using the intercepts to graph the boundary line, I see I'm going to run into a little bit of trouble, because solving the equation 400D equals 100, for example, would leave me with D equals 1/4. That's not going to give me the best graph. So I think what I'm going to do in this situation is simplify this a little bit so I can graph the boundary line using slope-intercept form. So I'm going to divide both sides of the inequality here by 50. So I'm going to have 8D minus W is greater than or equal to 2. And you can see that with this form of the model, it's going to be a lot easier to work with slope-intercept form. So let's graph the solution set. So I want to start by graphing the boundary line. And in this situation, what I think I'm going to do is take my 8D minus W equals 2 and solve for W, so I'll have an equation in slope-intercept form. So I'm going to add W to both sides. And then I'm going to subtract 2 from both sides of the equation. So I have, as my boundary line, W equals 8D minus 2. Now, since in this problem I'm talking about number of deposits and number of withdrawals, I just chose a coordinate system where I'm showing predominantly the first quadrant. The number of deposits and the number of withdrawals should be positive. The vertical intercept, or the vertical coordinate of the vertical intercept, is -2. It's not going to help me much to graph -2 withdrawals. So I want to find another point that satisfies this equation. Well, I can quickly see a point. For example, the ordered pair 1, 6 will satisfy this equation. 8 minus 2 is 6. So D is my independent variable in this case, and W is my dependent variable. So this is the number of deposits. Almost takes longer to label these graphs than it does to actually draw the line. Number of withdrawals. In this problem, I think I'm just going to use a scale of 1 for the number of deposits. So I've got 2, 4, 6. And for the number of withdrawals, when I graph this line, it's going to have a slope of 8. So I think I might use a scale of 2 on my vertical axis. So I have 4, 8, 12, 16, 20. We want a lot of money in the account. Okay, so now I have scaled my axes. Let me plot the point 1, 6. And I'm going to use a slope of 8 to get a few more points on the line. So 8 is 8 over 1. So I can go up 8 over 1. Up 8 over 1. So now there is my boundary line. And now we just point out a few things because I feel fairly certain it is the correct line. I see the vertical intercept is indeed at 0, -2, and also my horizontal intercept is at 1/4, 0. So here's my boundary line. Now I want to think about what solutions make sense in the context of the problem. So we started with the point 1, 6. This means that if one deposit of $400 is made and 6 withdrawals of $50 are made, then there'll be exactly $100 in the account. Well, how can we improve things for Logan? Well, we could put more money into the bank. So for example, if 2 deposits of $400 are made and he only withdraws $50 6 times, he'll have more than $100 in the bank account. Another thing we could do is, if 2 deposits are made, think about how many withdrawals, maximize the number of withdrawals he could make. So if I go up and get pretty close to this line, I see that, okay, if he makes 12 withdrawals after 2 deposits, he's still below this line. So my solution set here is going to be to the right or below this line. And in this situation, the number of deposits and the number of withdrawals will be greater than 0. So I'm really just looking at the ordered pairs that make sense in the first quadrant. Again, the only ordered pairs that make sense in the context of this problem are ordered pairs with integer coordinates. So let's talk about a couple of the solutions we just found. So what are some of the possible combinations of deposits and withdrawals? That was the question we were asked here. So if one $400 deposit is made and there are only 6 withdrawals, then there will be exactly $100 in the account. On the other hand, if we want more money in the account, the 0.26 tells us if 2 deposits are made, and only 6 withdrawals, then there will be more than $100 in the account. We also saw that with 2 deposits, 12 withdrawals can be made and still keep the balance above $100. There we go. We have stated a conclusion. We've talked about 3 possible solutions. It took a lot of words, but we're really trying to think about using algebra in the context of applications. So that's the end of lesson 19. In the last lesson in Math 60, we're going to review some material about linear equations and 2 variables.